Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at deformation and metamorphic rocks. So in this video we're going to think about what are some of the common metamorphic features that you will encounter when you look at metamorphic rocks. And this is going to correspond to section 8.6 of your textbook. So the first thing we need to do is we need to define what is a metamorphic rock. So a metamorphic rock is one of the main classes of rock, and it's formed when we take a pre-existing rock and we expose it to increasing pressure and temperature. So the thing is that rocks, as we know, are made up of minerals, and each mineral will have its own conditions at which it is happy. So there will be an upper and lower temperature limit and an upper and lower pressure limit at which our mineral is stable. The second we take our mineral outside this range, our mineral is going to become unstable. And when this happens, our mineral can do one of two things. It can melt. However, that's relatively uncommon in geology because normally pressure stops melting from happening. So that means there's only ever one option, which is the mineral can simply change into a new mineral which is stable at the new higher pressures and temperatures. So this process of taking one mineral and turning it into a new mineral which is stable under new conditions is referred to as metamorphism. And so the process of taking our original rock and turning it into a new rock with a new mineralogy is called metamorphism. So metamorphic minerals often are very distinct when compared to the types of minerals that we get in igneous and sedimentary rocks. So there's a lot of variation in metamorphic minerals, and that's because there's a lot of range in terms of what temperature and pressure conditions our rock can be exposed to, and there's a lot of variation in the chemistry of the original rock, because obviously that's going to affect what minerals we get. And so metamorphic rocks are often quite easy to spot because they will often have a range of very distinctive minerals which will only occur in metamorphic environments. Now, one of the other things that we can tend to see with metamorphic rocks is that they will often have some kind of texture to them, and this texture often forms in response to the rock being deformed. And so you can begin to see now how deformation and metamorphism tie together. So arguably one of the most common metamorphic textures that you'll come across is something which we refer to as cleavage. So cleavage is the result of minerals achieving a parallel alignment. So if you have the correct type of mineral in your rock, you can essentially apply a force to your rock and it will make the minerals align themselves parallel to each other. And we will see this at a hand specimen scale in the form of essentially a layering in our rock. So in our model here you can see we have a block of rock which consists of 5 distinct beds, and you'll notice that this block of rock is being compressed along the axis marked out here by these 2 blue arrows. And so in this model we're going to have our rock deforming in a ductile fashion. So when we compress our rock, it's going to buckle, so it's going to fold, and we can see the folds here marked out in this yellow-white layer and in this kind of pinky-brown layer down here. Now, another thing that's going to happen during this compressive event is that if you have the right types of minerals, they will begin to orientate themselves at 90 degrees to the direction in which the rock is being compressed. So as we can see in this block here, we have a rock which is being compressed from the front and from the back. This means that if we have the correct minerals, we can force those minerals to align themselves at 90 degrees to the compressive force, so that would be top to bottom. And so we see this forced alignment of minerals in the form of cleavage. So here we go. So this picture here is actually summarizing this diagram up here beautifully. So we can see here we have a fold, so we know our layer of rock is being compressed, and the fact that we have a fold here is telling us that our layer of rock is being compressed from the left and from the right. So we know where the compressive force is coming from. Now what you'll notice is that this layer, or this sequence of rocks, has a distinct vertical texture to it. This is the cleavage. And this has been produced by minerals being forced to align themselves at 90 degrees to the direction in which the rock is being compressed. So we know in this particular image the rock is being compressed from the left and the right, and this means that the minerals will therefore orientate themselves top to bottom. So a cleavage is just essentially a reflection of the compression of a layer of rock. Now, we are most likely to be able to form a cleavage in a rock that has either platy minerals or elongate minerals. So a platy mineral is a mineral that has a three-dimensional shape a bit like a piece of paper. So you're looking at a mineral that's rather thin, a crystal should I say, that's rather thin, but has a broad shape to it. An elongate mineral would have a shape similar to that of a pencil. So you would have a mineral that would be quite long and quite skinny. In both of these cases, if you apply sufficient force to either a platy mineral, or an elongate mineral, you can force them to align themselves parallel to each other, and this can lead to the formation of a cleavage. So we can see the same thing happening here. So we can see our cleavage is orientated approximately north-south, and this is going to be in response to our rock being compressed once again from the left and from the right. So are there any other ways in which we define cleavage? Well, yes, there are. Cleavage can generally be split into two broad groups: foliations and lineations. And so what we're going to do now is we're going to look at some rocks which show a foliated cleavage. So the first type of foliation which we can see here is a very specific type of foliation which is called a schistosity. And schistosities are associated with a very specific type of metamorphic rock which is referred to as a schist. So schists are metamorphic rocks which are dominated by a group of minerals which we call micas, and you've already come across a couple of these mica minerals in the form of biotite and muscovite. So in this particular image here, you can see we have a rock which has a very distinctive shiny silvery appearance. It looks a bit like tinfoil almost, and that's because this rock is extremely rich in the mineral muscovite. So what's going to happen is muscovite is a platy mineral, so it has very thin crystals, but those crystals are rather broad, once again, like a piece of paper. And so if we apply enough force to this mica-rich rock, this muscovite-rich rock, it will force the mica crystals to align themselves parallel to each other. Now, when we look at this alignment in 3 dimensions, what we're going to see is something that looks like this block diagram here. So remember, our minerals are platy. So this means that when we compress our rock, for instance in this model, if we're compressing our rock from the top and the bottom, we're going to force our platy minerals to orientate themselves at 90 degrees to that compressive force. So in this case, left to right. So what you'll notice is the platy minerals are all being forced to align themselves parallel to each other, so we know we're going to have a foliation which is running across our rock like so, at 90 degrees to the direction in which our rock is being compressed. Now, because our minerals are platy, so they're like a piece of paper, we're going to be able to see the foliation on this face of our piece of rock and this face of our piece of rock. However, you are not going to be able to see the foliation on this face of our piece of rock. So just imagine a stack of pieces of paper. When you look at your stack of pieces of paper, what you can see is you can pick out the individual pages on the front of your stack. You can pick out the individual pages on the side of your stack. But if you looked straight down onto your stack, you would not be able to see any kind of indication that your stack was made up of multiple pages, would you? So this is exactly the same thing that we see in a foliated rock. We can pick out the foliation on one face, we can pick out the foliation on the other face, but if we look top down, you can't see the foliation. So the next type of foliation that you might encounter is called a gneissic foliation. And gneissic foliations are associated with a type of metamorphic rock which is referred to as a gneiss. So that's G-N-E-I-S-S. So gneisses have this very distinctive pattern to them of light and dark bands, and you can see that illustrated quite nicely in this picture here. So the dark bands are made up of ferromagnesium minerals. So these are minerals which contain lots of iron, magnesium and calcium, and they're going to be naturally quite dark in colour. The lighter bands, on the other hand, are going to be made up of non-ferromagnesium minerals. So these are going to be minerals which are rich in sodium, potassium, silicon and aluminium. So we're looking at minerals like sodium-rich plagioclase feldspar, potassium feldspar and quartz. So when we look at this gneiss exfoliation, we will see a similar pattern to the schistosity. So if we took a piece of gneiss, or a block of gneiss, and we looked at it, we would be able to see the gneiss exfoliation on one face. We would be able to see the gneiss exfoliation on another face. But if we look down from the top onto our block of rock, we would not be able to see the gneiss exfoliation. And this once again is a reflection of how the minerals are arranging themselves. It's relatively common in gneiss exfoliations for these darker bands to be dominated by the mineral biotite. And biotite, once again, like muscovite over here, is a platy mineral. So the crystals are going to have a shape like a piece of paper. And so exactly the same principle that we were discussing for the schistosity over here will also apply to the gneiss exfoliation. So other rocks that will show foliations are rocks which have undergone ductile deformation. So in this case, you can see we have a rock which once upon a time was a conglomerate. And so we can see that we have our clasts here, and the matrix itself is marked out by this darker material. Now the rock has clearly been compressed because these clasts initially would have been somewhere between spherical and elliptical in shape. But you can see now they've quite clearly been flattened out to give us this disc-like morphology. So that's a clear indicator that this rock has undergone deformation. So what you'll notice is, as part of this deformation event, the squishing force, which has been coming in from the top and the bottom, so the compression's coming in north-south, has essentially flattened out our clasts and made them orientate themselves approximately east-west. And so once again, if we were to look at our meta-conglomerate in a three-dimensional block, we would see, right, these dark lines are going to represent our clasts. So we would see clasts that were orientated east-west, we would see clasts that were orientated like so. But if we were to look from the top down onto our meta-conglomerate, we would not really be able to see the alignment which we could see on the other two sides. We can also see foliations which are the result of shearing. So if you remember, in the case of shearing, we have a block of rock and we're trying to move the ends of the block of rock in different directions. And so this means that the central area of our block of rock is going to be deformed. It's going to be sheared. It's going to be stretched and pulled as part of this shearing process. And as the rock gets sheared, it can actually force the minerals, it can stretch the minerals and make the minerals bend, essentially to align themselves. And so we can see this texture right here. We can see, in this case, the shearing is orientated left to right, and you can actually see the rock has been sheared when you look at these features here. Now these are referred to as algons. So you can actually see a nice one quite here. You can see that it doesn't have a spherical shape. In fact, it has one of these lozenge shapes to it. It's narrow at the end, it widens up, and then it narrows again at the other side. So the presence of these algons is a common indicator to geologists that the rock is being sheared. And so that's how we know that this is a sheared rock rather than a foliation that's formed through another process. And so this shearing has forced the platy minerals, once again, mostly biotite probably, to align themselves parallel to each other, and this has resulted in the formation of a metamorphic foliation. Alright, so the next type of metamorphic texture which we will commonly come across is called a lineation. Now lineations are formed by different types of minerals. So in the case of foliations, the foliation is very often the result of the presence of platy minerals. So once again, platy minerals are very thin crystals which are quite broad, like a piece of paper. In the case of rocks which show lineations, the minerals are normally quite elongate. They're like a pencil. They are long and slender. So this Sharpie would be a good representation of the kind of shape which we would expect our crystals to have. And you can see them here in this rock. So you can actually see a crystal right here that has this long, thin morphology to it. And so if we can force these elongate crystals to align themselves parallel to each other, we are going to end up with another metamorphic fabric. So what we can see in this instance is we can see a weakly lineated rock. We can see that these crystals of this blue coloured mineral, which is probably the mineral kyanite, I can't be 100% certain, but it looks like it, these crystals are orientated approximately top to bottom. So we can see them here, here, we can see them here, we can see them here. So we have a weakly lineated metamorphic rock. Now, this particular rock is actually a much better example of what a lineated metamorphic rock looks like. So in this case, as these lighter crystals have been growing, they've actually been stretched. So the rock is being actively sheared as the crystals are developing, and this causes the crystals to become stretched. It draws them out, a bit like pulling a piece of silly putty. And so this has resulted in this rather beautiful texture where you can quite clearly see the lineation marked out along the length of the outcrop here. Now, when we look at the end of the outcrop, you can't actually see the lineation. All you see are the ends of the crystals. So if we look at this block diagram down here, we can see what a lineation looks like in 3 dimensions. So remember, the crystals we're dealing with are essentially like pencils. So imagine, if you can, you're holding a bundle of pencils in your hand. Now, if you look at the bundle of pencils from the top down, you can see the pencils quite clearly, can't you? You can see the lineation produced by the pencils. If you look at your bundle of pencils from the side, once again, you can see the layering quite clearly. However, if you look at your bundle of pencils from the end on, well, you're not going to be able to see the lineation. All you're going to be able to see are the ends of your pencils, or in the case of the lineation, the ends of the crystals. And so you can see there's a distinct difference between lineated metamorphic rocks and foliated metamorphic rocks. So if I just go back to the previous slide, in the case of foliated metamorphic rocks, because the minerals are platy, so they're like a piece of paper, we can see the fabric on the front and on the sides, but we can't see the fabric on the top. In contrast, a lineated metamorphic rock will show the fabric on the side and the top of the outcrop, but it will not show the fabric when we look at the texture end on. So you can see there's a distinct difference, and this distinct difference is a reflection of the shape of the crystals. In foliated metamorphic rocks, we're dealing with platy crystals. In lineated metamorphic rocks, we're dealing with elongate crystals. Now, we can also form lineations due to shearing, just like we can with foliations. However, in the case of lineated metamorphic rocks which are produced by shearing, once again, we have long, slender crystals, and the shearing force is forcing these crystals to align themselves. So we're dealing with crystals that have a different shape. And so this is how we can distinguish between foliated metamorphic rocks and lineated metamorphic rocks. So are there any other types of structures which we will find in metamorphic rocks? Well, yes, if we have a metamorphic rock that hasn't been particularly heavily metamorphosed, we can on some occasions actually retain the original structures of the precursor rock. So in this case, we can see we have a sequence of rocks here, and the original rocks were split into these darker bands and these more kind of rusty coloured bands. And we can see that this band here in particular has a rather undulating upper surface to it. So what we have here are ripple marks. So these are ripples which were part of a sediment which was then lithified and turned into a rock, and then that sedimentary rock was metamorphosed as a result of increased heat and pressure. So we can easily pick out these original structures. Now, most of the time, if your metamorphic rock has been strongly metamorphosed, so that means it's been taken to quite high temperatures and pressures, it can often lead to these original textures being destroyed. So typically you'll only have these original textures persisting in your metamorphic rock if it is relatively low grade. Another type of texture which we might commonly see in metamorphic rocks are shear zones. And as we've discussed, these are the areas where a rock is being actively sheared, and typically one side of our block of rock is trying to go one way, the other side of our block of rock is trying to go the other way, and this means that in the center of our block of rock we have this build-up of stress, and this build-up of stress can essentially cause the minerals to become smeared out almost. So if we look at this metamorphic rock here, we can quite clearly see we have a cleavage coming down like so, and on the lower side we can see we have a cleavage coming down like so. Now, because either side of this block of rock is trying to move in opposite directions, what happens is this area in the middle here is where a lot of the deformation, a lot of the stress and the strain build up. And so the minerals in this region here are going to be actively deformed, and we can see this deformation in the form of a shear texture. So we can see that the minerals in this central region are orientated approximately left to right. So if we imagine a situation where this block of rock wants to go that way, this block of rock wants to go to the left, and it causes the stresses to build up in the center right here, and the fact that this rock's going this way and this rock's going this way causes the minerals in the center to be pulled over and orientate themselves left to right. So another texture that we might see are folded pebbles, and this is only commonly associated with metamorphosed coarse-grained sedimentary rocks. So think of conglomerates and breccias that have been metamorphosed and they've entered a region of ductile deformation. So we can see that these very quartz-rich regions here were once upon a time clasts in a conglomerate, and this conglomerate has been taken to relatively high temperatures and pressures. It's undergone ductile deformation, and we can see that as a result of this ductile deformation, these clasts essentially have been smeared out and they've been folded. So what we have here is a metamorphic rock that's undergone a relatively high degree of ductile deformation, resulting in the clasts becoming warped due to that deformation. The final type of metamorphic texture which we will commonly come across is what's referred to as a deformed foliation. So lots and lots of different metamorphic rocks will have either a foliation or a lineation. And what will happen is this foliation or lineation will form in response to some kind of tectonic stress, but then it's not uncommon for the deformation of the rock to continue over a long period of time, and this can actually lead to our foliation or lineation becoming folded. And you can see this quite nicely in this particular outcrop here, where you can see we have a rock that has very distinct light and dark bands, and you can track the layers, and you can quite clearly see that yes, they have been folded. So what we have here is a lineation or foliation that's undergone later deformation after the foliation or lineation formed. All right, thank you for watching everybody, and have a good day.